fundamental theorem for line integrals. And then after that, we're going to get into Green's theorem. So essentially, if you're integrating the gradient of a function dx, then the integral is just going to be f of the endpoint of the path minus f of the beginning point of the path. And a function f, or rather, a vector field f is conservative if and only if this. But what that means is a vector field is conservative if it is the gradient of a function f. Okay, so if this is the gradient of some function, then it's called conservative, and this is only going to happen if these partials match up. Now, the reason for that is that if it is the gradient of a function, then that means that so if this is a gradient of a function, so if this is the gradient of a function, then that means that partial of f with respect to x, it's going to be partial of x with respect to x in the I direction, plus the partial of q with respect to y in the j direction. Okay, and this basically is partial of f with respect to x. And then the q part, wait, this should be an f here, sorry about that. Then the q part is the partial f with respect to y. So if this field is the gradient of some function f, then the p part is this, the q part is that. So if you take the partial of p with respect to y, you're going to get the partial of f. You're going to get the second partial of f with respect to x and then y. And then here, if you take the partial of q with respect to x, which is this part here, you're going to get the second partial of f with respect to y and then with respect to x. And the thing is that those two are going to be equal to each other, because as long as they're continuous partials, which always happens, then they're going to be equal. So then these being equal is the same as that being equal right there. Okay, so this equation is just that. Okay, so anyways, two things. This right here and then this right here, you can tell if it's conservative if and only if that. So let's get to the exercises. Number one, you have a table of values with the continuous gradient, and then you want to find the integral of this, okay? So according to the formula, that's going to be f of r of b minus f of r of a, because you're integrating a gradient, and this is the fundamental theorem for line integrals. Okay, so let's see, what is r of b, what is r of a, what is b and what's a? Well, there's our a and there's our b, right? So, and then this is our r right here, this function, right? These two functions right here. So r of b is going to be r of 1, which you're going to plug a 1 in for here, and then you're going to plug a 1 in here. So that's 2, 2. Okay, so that's f of 2, 2. And then 2, 2 is 6. So that's 6. And then the other piece, r of a, that's going to be r of 0. And so you plug in zeros for here and here. So 0 cubed plus 1, comma 0 cubed plus 0. And now it's going to be 1, 0. And that's minus f of 1, 0. which is, here's 1, there's 0, so that's this one here. Okay, and so then your answer is 5 for the first one. Okay, so the interesting thing is it doesn't really matter what the path is. So we never had to take the derivative of this or this. We never had to plug these values. We never had to plug these expressions into the equation, just the first and the last point. And that's what happens when you have a conservative vector field. Okay. So let's get to number 2 here. Okay, so it says determine whether or not f is a conservative vector field. If it is, find a function f such that. Okay, so this is what f looks like right here. It's just two variables, and to determine whether it's conservative or not, it's this right here. dp dy, if dp dy equals dq dx, according to the explanation that I gave you guys. So this is dp dy equals dq dx, and then this is p and that's q. Okay, so dp dy is what? If I take the partial of this with respect to y, what do I get?
Don't you get negative sign?
The partial with respect to y?
E to the power of x
I can't
plus
read it.
cosine y.
Oh, cosine y. Okay, you can't read it?
No,
Darn it.
I had it on half a screen, so I had to zoom in. I can see it now. It looked like a G to me, but
Oh, okay, and then partial of q with respect to x.
It's
That's
e
e
to the
q.
x and cosine y.
Okay, and so these are equal, right? That's equal to that, so it's conservative. So yes. Which means we have to do more work. Yay. Okay, so here's what you, if that's the case, then what happens is this first one, pay attention really carefully here. It's the partial derivative with respect to x of some function f. Okay, and the second one, the partial of q is this, not q. The partial is the partial of f with respect to y. Like that. Okay, so partial of f with respect to x is this. Partial of f with respect to y is this. Okay, so what you need to, what we do now is we figure out what that y is. So now, so you kind of take an antiderivative, but anti-partial derivative. So you think what function f, when I take the partial with respect to x, would give me this. Okay, so just like integrate in x, so that's e to the x. And then this is x sine y. Okay, now this is, now what would, I'm going to add another function g of y to that. Okay, because if there's like a whole function that just has y's in it, I mean, it could have like y's all over the place. But if there's no x's, then you take the partial with respect to x, it's just going to be 0, it's just going to go away. Okay, now, that's what we get from here. From this one here, you take the antiderivative with respect to y. So this is y e to the x And then this one's going to be x sine y. And then this could have a function in x. Now, at this point, what you need to do is figure out, you want to find an expression of f that equals both of these. Now, in this case, this is exactly the same as that. And so that's just all it's going to be. Okay, that's it. So we don't, this one wasn't needed, that one wasn't needed. Okay, but sometimes what will happen is you'll have a function, you'll have a bunch of stuff in y over here, and so you just add that on to the end, and that was that. Or you have something in x over here, and you add that on to the end. Okay, so notice that I'm not like doubling this, I'm not adding these together, I'm just taking the minimum stuff, I'm taking exactly what's required to satisfy that and that. Okay, so let's put this function in and see if that gives the right answer. Okay, it works over here. Okay, so that's another exercise. Determine whether f is a conservative field. So again, this is our p and that's our q, right? So we check it by taking the partial of p with respect to y and the partial of q with respect to x and seeing if those are equal. Okay, so this is just with respect to y. So I'm going to get negative e to the x sine y. What's the partial of this with respect to x?
E to the power of x sine y.
Times sine y, right? Okay, these are negatives of each other. Is that okay? Are they equal then? Are these equal?
No, they're
They're not
different.
equal. So
It doesn't exist. Yeah.
Does not exist. It's not a conservative field. Okay. It's not a conservative vector field because it can't be. Because those are different, so that means they can, these can't be this can't be a gradient of any function. Okay, so number 4. What's happening here is you're starting from this point here and you're going to that point, and they're telling you 3 different paths. Okay, so this is like path 1, and this is like path 2 right here, going this way. And then this is path 3, going that way. Okay, and so it starts at 1, 2, and ends at 3, 2. And so part A says explain why it has the same values for all 3 curves. This is our P, that's our Q. If we take the partial of P with respect to Y, we get 2x. And if we take the partial of Q with respect to x, we get 2x. So that means that this field is conservative, right? Which means it doesn't matter what path you choose because it only depends on the end point and the beginning point. So the answer to A was the last one. So the vector field is conservative. Okay, then the second one is asking what is that common value? So what should we do for that? What should we do to figure out what the common value is?
If you take the partials, oh, no.
So, so if it's conservative, that means that it is the gradient of some function, and that means that the partial of with respect to x is 2xy. The partial of that function with respect to y is x squared. Okay, so if I integrate with respect to x, what do I get?
Two y.
That's the derivative. I want to go the opposite way.
And then 2x. Oh, use x squared y.
Yeah, x squared y. Okay, but then you could have a function in y too, right? Because if you take the partial of this with respect to x, this goes away. Okay, now integrate this in y or find antiderivative. That's also going to be x squared y. Then I could also have a function of x. But this is not needed because here these are all the same. So what's my potential function? What's my potential function going to be now?
X square y and
Yes,
t
that's
of
it.
x.
That's it. X squared y. That's it. Because this right here satisfies that and that. Okay? So that completely works. Okay, now, the integral okay, so we're going from here to here. That's going to be f of the endpoint minus f of the beginning point. And this f right here. So 3 squared times 2 minus, and then this is 1 squared times 2. So that's what, 9, 18 minus 2, which is 16. Okay, any questions about that? Okay, so let's go on to number 5. And here we have three. It's three-dimensional vector field. So there's the I component, a j component, and a k component. And the first part is to find the function f so that it's the potential. And such a function would have to satisfy the partial of f with respect to x is going to be this first function, yz. The partial of f with respect to y is going to be the second function here, xz. And the partial of f with respect to z is going to be this last one, so xy plus 4z. So it's a function in x, y, and z. Okay, so what function has a partial that's y with respect to f is with respect to x is yz? So take an antiderivative here of this. Sort of do some antiderivative stuff here. And what would work?
The y set x.
What's that? Just add an x? Like that? So when you take the partial with respect to x, you're just going to get yz, right? Okay, but in this case, I'm going to call it g1. I could also have a function in the y and z. If there's just a bunch of y's and z's in the equation, in this right here, then it's going to, when I take the partial, it's going to be 0. Okay. What about this one? How can I get, what can give me this?
Just add a y.
Yeah, so x, y, z, right? But then I'm going to have another function in x and z. Now what can give me this? Or what can give me this? When I take the partial with respect to z. Just focus on this one.
Is set.
X, Y, Z, right? And what about this one? What's an antiderivative of 4z with respect to z?
Two z squared.
Yeah, 2z squared. And then I could potentially have a function in x and y. Okay, now, so what is my function going to be? What's the simplest function that is that and is that and is that? Well, it's got to have this term, right? So if I put that there, that takes care of that, that, and that. Just one of these. Don't make it 3. Don't make that 3 because that's like totally wrong. Okay. But then what else am I going to need? Okay. But then I have this piece here, right? So I'll need that. Okay. Now can that be made equal to this? And the answer is yes, because I can make this equal to 2z squared, right? And that can be made equal to this by making this equal to 2z squared. And this can be made equal to this by just making that 0. Okay, so that will just make that 0, and that will become 2z squared, and then that make that 2z squared. Okay, and then so there's our function right there. So that's the answer for the part A. And then for part B, we want to find this right here, right? Now, it's saying the line segment, okay, C is the line segment from this point to that point, right? But we don't have to do a parameterization. Okay, because it really doesn't matter what path it took, as long as the only thing that matters is that this is the beginning point and that's the end point. Okay, so the integral wait a minute. I can't believe it. I left this off. Okay, Okay, so that's going to be equal the end point minus the beginning point. Okay, so usually when you do line integrals, it matters what path you take. Usually it matters, because we've done other exercises and it matters, and you have to do this all out. But it's just in this special case where what you're integrating is the gradient of some function. And then you find that function, and then you can just use this. So x, y, z, that's what, 4 times 5 times 3 plus 2 times 3 squared minus, and then this one is going to be 1 times 0 times -1 plus 2 times -1 squared. Okay, so I get, I believe this is 78 minus 2. Okay, so 76. Okay. Okay, so let's go to the next one, number 5. And here we're supposed to find the work done by a force field F and moving an object from P to Q. Okay, so this F, if you take the partial of P with respect to Y, you're going to get 0. And if you take the partial of Q with respect to X, you're also going to get 0, because there's no Y's in here, there's no X's in there. So that means that this is a conservative vector field. And so we find the potential function by solving these equations. Okay, so a partial of f with respect to x is equal to the first part, which is x cubed, and then the partial of f with respect to y is equal to y cubed. Oh, by the way, the work is going to be equal to the integral f dot dr, okay, which is just like what we're just doing. Okay, so finding the potential function is the route to go. And what function? So what function will give me x cubed when I take the partial with respect to x?
One over 4 x cubed off of.
Exactly. Okay, plus some other function in y, right? Okay, then over here, I do the same thing. I have y to the 4th over 4, right? Plus some function in x. Okay, so what function f will be equal to this and simultaneously be equal to that? Well, you're going to need that, and you're going to need that. And this one doesn't appear here, but they can be this. This one doesn't appear here, but it can be this. Okay, so this will do it. This will do it right here. And so the work, which is that integral here, will be f of the end point, 2, 2, minus f of the beginning point, 1, 0. So that's 2 to the 4th over 4 plus 2 to the 4th over 4 minus, and then we have 1 over 4, or 1 to the 4th, or this is 1 over 4, plus 0 over 4.